In this video, I'm going to show the image of why we need a DFT in a SerDes system. In any product, we must make sure there are no hidden manufacturing defects to cause the malfunction or reliability, no matter the hardware or software. Therefore, we must add testability features as much as we could for product self-validation, which helps the product easier to develop under the manufacturing test of ensuring no manufacturing defects or malfunction risk. In this DFT video, we will only focus on the design for testability DFT in the SerDes system, especially the front-end analog circuitry. Since we need to know why DFT in a SerDes, we must look at what could be wrong to know where we should add the testability. This is a simple one-line C-link. The transmitted information D-in is sending through a timing flop, the following inverter as a buffer to drive a piece of wire. On the receiving side, the inverter and the receiver is a pre-buffer to recover big enough signal level, such that a flip-flop can regenerate back to a correct digital data D-out under enough digital timing. Do you see anything that could be wrong with the one-line C-link? The goal of the one-line data communication is to receive the same bits as what we have sent. In other words, we want the D-out to equal D-in. And how could we check if we meet the required BLA? Think about the tracker images for 5 seconds. Bingo! We must add an error tracker at the D-out to make sure the receiver data is correct, which is the same as what we have sent. Unfortunately, we cannot exactly know the correct random data we've sent. After the D-in went through the timing flop, buffer, channel, rebuffer amplifier, and the timing flops of the serial interface, it could be wrong in every place, and there's no available correct D-in sent from the file and TX for the D-out as an error criterion. So, the error tracker must be a self-container tracker through the D-out directly. Think about the shooter image for 5 seconds. Correct. If the random data cannot realize a self-contained error tracker easy, why don't we apply a pseudo-random binary sequence PRBS to test the serial digital interface, which can be easily generated through a linear feedback shift register LFSR as shown here. However, the PRBS pattern must be close to the data pattern used in a protocol's data transmission. Otherwise, the test result will not applicable and valid. The beauty of the PRBS pattern is a good approximation of most protocols' data format. For example, in a few standards like the DisplayPort RBR up to HBR3 and PCIe Gen 1, Gen 2, the AB10B encoding is used, which maps 8 bits words to 10-bit symbol, and it's a PRBS 7 approximation. For Ethernet 10G base KR or 40G base KR, it maps 64 bits data to 66-bit symbol, and it's a PRBS 31 approximation. Others, like the PRBS 9, could be used for the SFP Plus test, and the PRBS 15 is often used for jitter measurement. Lastly, the PRBS 23 is for the SDH SoundNet test and can also support some test equipment. After knowing the LFSR can generate the PRBS pattern easy, how can we implement the PRBS tracker? Right, we could compare or exclusive or XOR both raw input data D-out and the D-out after a linear feed-forward shift register. If the input data D-out is a PRBS N pattern without any error, the XOR output would always be 0, which shows an error-free DR. Unfortunately, there's one P4 state such that the PRBS tracker will make a wrong decision. Think about your all ones or all zeros images for 5 seconds. Bingo! If all zeros went through the shift register, the output pattern stuck to a 0 state, so the output would be 0. Unfortunately, the input or D out is 0, so the output of PRBS tracker would be probably 0, which is error-free mistakenly. On the other hand, if all ones went through the LFSR, even though the shift register output is 0, the PRBS tracker output is 1 to report an error. So, how can we avoid or mitigate this issue if the received data are all zeros? Correct. If all zeros would be the issue, we can intentionally insert any zero or error in the bit stream at either pass before the tracker and see if the expected error occurs. Here, if yes, we can include that all zero state, but if we don't see any errors at the tracker after inserting one or more zeros into the bit stream, which means that all zero state exists, and we conclude that error-free was a false test result. After knowing the PRBS gen and tracker could help us test the correctness of the received bit, what else could be wrong through the more complete front-end C-link image here? Think about the signal integrity images for 5 seconds. Correct, the channel could be wrong. Most of the channel's impairment images would be insertion loss and return loss because of the media materials and interface discontinuity. To exclude the possibility of the received error because of the channel, what can we do? Could you think about the SerDes or bidirectional images for 5 seconds? Bingo! On any one side of the SerDes chip, we should have both TX and RX in a bidirectional link transmission. So we can just send the data from the near-end TX to the near-end RX such that the channel and connectors were included from the data transmission. If we see error-free from the full TX to the RX loopback path, we can conclude the channel impairments could be the source of error in the previous complete link transmission. By simply adding the switches between the TX and RX on one side of the chip, the loopback implementation is easy enough for a production test using automatic test equipment ATE. So we might also call it an ATE loopback, which should support a full speed, specify maximum data rate to reduce the test cost. If the ATE loopback still shows an error, what else could be the issue? Think about the analog images for 5 seconds. Yes, we could suspect the TX driver swing was not big enough to provide error-free condition, or the RX COE has neither good enough input sensitivity nor SNR for the sampler or comparator to make the right decision. So we can bypass the front-end analog circuitry at the TX driver and RX COE and see if the error occurs. If the error still occurs, we might know the issue is with the digital circuitry. On the other hand, if the loopback of the front-end bypass is error-free, we know the issue could be the TX driver or the RX COE. But how do we narrow the issue down afterward? Bingo! We could keep reducing the components in the data transmission by bypassing more blocks. For example, we could bypass the CTOE front-end but use another auxiliary or simplified front-end amplifier. Again, If the error still exists, we know the issue must be the TX driver, including all the high-speed predriver and logic. If not, we might know the issue is the CTOE and can do further debugging on it. Please be advised that there are still lots of design for testability DFT and method images in a SerDes system not shown here. The goal of this why DFT video is to demonstrate why the DFT is very important in addition to the normal operation mode of the SerDes. Through the DFT images, we could further understand how the DFT can help us debug or validate the SerDes functionality quickly and reduce the testing cost in production without reducing the test coverage and precision. We could show other DFT images in other videos if needed, according to everyone's feedback. Here are the summarized images of why you need a DFT in any SerDes system. To verify or test a bit array in a C-link through a data transmission easy for multi-protocol products, a PRBS N pattern with the word length of n bits and the sequence length of 2 to n minus 1 bits would be a good approximation of those protocols pattern. Since the pseudo-random sequences are generated through a linear feedback shift register, we can implement the PRBS checker in such a simple shift register way as a self-contained checker. To debug or validate the link's performance or reliability in each block, we need to rearrange the link components a bit during the bit array testing. For example, the whole C-link could have a very high bit array up to 1e-3. First, if we remove the channel and interface connectors by connecting both near-end TX to the near-end RX and see the bit array drops to 1e-9 or even below, then we may know the signal integrity impairments from the channel or connectors could be the source of high bit array. On the other hand, if the bit array is still high, around the order of 1e-3 at the ATE loopback path, we might know the TX driver or the RX CTOE cannot boost enough swing or SNR at the sampler input if we bypass the TX driver and RX CTOE and the test digital path works fine with very little bit array. Otherwise, if the digital loopback shows high bit array, then that could be some digital timing variation. Lastly, if we know the front-end analog circuitry could be the source of error, we could even bypass the CTOE and check the TX driver with the simplified RX buffer, such that we can finally exclude the CTOE and identify if the TX driver is the error source. Again, all those DFT images will be either show you the importance or the debug process during the testing validation. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.